Welcome to this explainer. If you're a focused learner looking to understand the absolute foundation of all global network communication, you're in exactly the right place. Today, we're cracking open the invisible architecture that runs the modern world. Think about this for a second. Right now, your device is connected to a server that could literally be thousands of miles away. It doesn't matter what brand your phone is or what country the server is sitting in, it just connects flawlessly, grabs the data, and displays it to you. But how does a message actually make that journey across a massive, chaotic, global network without a single one or zero getting lost or corrupted? Well, the answer is a universal layered framework called the OSI model. Okay, let's dive into this. We've got a quick 5-part roadmap for today. First, the universal language of networks. Second, breaking down the layers. Third, how data actually travels. Fourth, OSI versus TCP/IP. And finally, the blockchain connection.
Section 1. The Universal Language of Networks.
So if we rewind to the early 1980s, the networking world was basically the Wild West. You had companies like IBM and Honeywell building their own proprietary systems, meaning devices from different manufacturers simply could not communicate. It was like every computer spoke a completely different language with no translator in sight. Recognizing this massive roadblock, the International Organization for Standardization, or ISO, stepped in. In 1984, they developed the OSI model, which gave us a universal 7-layer framework so any device anywhere could finally talk to each other.
Now, you might be wondering, why layers? Why not just build one massive system to handle the whole shebang? Well, it's all about separating complexity. Think of it like a courier service. When you drop off a package, the person at the intake desk doesn't need to know how the delivery truck's engine works, right? Intake, sorting, and delivery all have their own specific jobs. Layered network architecture works the exact same way. It simplifies the complexity, lets different vendors build parts that actually work together, and makes troubleshooting incredibly efficient.
Moving on to Section 2, breaking down the layers.
All right, here is the entire stack, from layer 7 all the way down to layer 1. And to help you memorize this instantly, we've got a classic mnemonic trick for you. All people seem to need data processing. That's application, presentation, session, transport, network, data link, and physical. When you send data, it starts at the top at layer 7 and works its way down. When you receive data, it comes in at the bottom and travels back up. Simple as that.
Let's start at the very bottom with layer 1, the physical layer. This layer really only has one job, transmitting raw bits, just single zeros and ones. It honestly doesn't care what the bits mean, it just moves them. It converts your data into fluctuating electrical voltages for copper cables, pulses of light for fiber optics, or radio frequency waves for your Wi-Fi. It's entirely grounded in the physical hardware.
Moving up one step, we hit layer 2, the data link layer. If the physical layer is the road, the data link layer provides the traffic rules. It takes those raw bits and organizes them into structured packages called frames. It also checks for errors, like maybe a flip 0 or 1 from some wireless interference. Crucially, this layer uses permanent hardware-embedded MAC addresses to ensure data gets delivered correctly to devices on a local network, usually routing those frames through devices we call switches.
But what happens when you need to leave your local network and travel across the globe? That's where layer 3 comes in, the network layer. This is basically where data gets its passport. Instead of permanent physical MAC addresses, this layer uses logical, hierarchical IP addresses. Your data is packed into what we call packets, and specialized devices called routers read that destination IP address to figure out the absolute best path across dozens of interconnected networks to reach its target.
Now, what's really interesting here is layer 4, the transport layer, which handles end-to-end delivery. At this layer, you have a crucial choice between TCP and UDP. TCP is the cautious courier. It establishes a solid connection, requires a literal receipt or acknowledgement for every piece of data, and retransmits anything that gets lost. It's perfect for web browsing or blockchain. UDP, on the other hand, it's like firing your data out of a t-shirt cannon as fast as possible without waiting for receipts. There are no delivery guarantees, but it's blazing fast, making it absolutely ideal for live video gaming or streaming.
Finally, we reach the top 3 layers, which are the closest to you, the user. Layer 5 is the session layer, which keeps the active conversation alive, kind of like maintaining your login state on a website. Layer 6 is the presentation layer, acting as the translator. It formats data and, vitally, handles encryption, like TLS, so your data stays secure from interception. And at the very top is Layer 7, the application layer. This provides the network protocols like HTTP for your web browsing and DNS, which basically acts as the Internet's phone book.
Section 3. how data actually travels. So, the downward journey of your data is called encapsulation. Think of it like putting a letter into progressively larger envelopes. Your application data gets passed down to the transport layer, which chops it up and adds a header, turning it into a segment. The network layer wraps that segment in an IP header to make a packet. Then, the data link layer wraps the packet in a MAC address header to make a frame. Finally, it's converted into raw bits at the physical layer to be blasted across a cable or Wi-Fi signal.
And when those bits arrive at their destination, the exact reverse process happens. We call this decapsulation. The receiving device reads the frame header, strips it off, and passes the packet up. The router reads the IP header, strips it, and passes the segment up. Each layer only reads its specific envelope and completely ignores the rest. Step by step, the headers are unwrapped until the pristine original data is handed right over to the receiving application.
Let's make this concrete. Imagine typing google.com into your browser. Layer 7 uses DNS to find the IP address and HTTP to ask for the page. Layer 6 encrypts your request via HTTPS. Layer 4 slices it into TCP segments. Layer 3 slaps the IP address on there to route it. Layer 2 frames it for your local Wi-Fi router, and Layer 1 turns it into radio waves. Google Server catches it, decapsulates it, and sends the web page back. You've got all 7 layers working in perfect harmony in a fraction of a single second. It's wild.
Section 4. OSI versus TCP/IP.
So, the crucial point here is this. The OSI model is a brilliant conceptual reference map, but TCP/IP is the actual implementation that runs the modern internet. TCP/IP takes those 7 OSI layers and just consolidates them down into 4. It bundles the top 3 layers into one, application layer, and the bottom 2 into one network access layer. You'll use OSI to learn, design, and troubleshoot, but the real-world infrastructure actually speaks the 4-layer TCP/IP standard.
And finally, Section 5, the blockchain connection.
And this brilliantly illustrates why all of this matters for the future of technology, especially when we look at decentralized systems. Blockchains often feel like pure magic, right? But they are entirely dependent on this legacy networking stack. When a node in India broadcasts a Bitcoin transaction to a node in Germany, the Bitcoin protocol itself lives up at Layer 7. But to get that transaction across the world, it relies on Layer 4 TCP to ensure the message arrives fully intact. It relies on Layer 3 IP routing to navigate the global internet, and it relies on Layer 1 cables and fiber optics to physically move the data. The security and speed of a blockchain are just completely intertwined with the physics and rules of these lower networking layers.
Which leaves us with a fascinating thought to close on today. We just saw how the cutting-edge magic of decentralized networks relies completely on a highly structured, decades-old networking science. It really makes you wonder, what other legacy protocols and established frameworks are quietly holding the keys to the next great leap in our technological future? Think about that, and I'll see you in the next Explainer.